Okay, so we are online. So let us start. So welcome to the 14th lecture of this course on solid mechanics. And today we will be continuing from where we left in our last lecture, and that was lecture 13. So if you remember, in lecture 13 we were talking about volumetric strain, and that part was complete. And then we started our discussion on local rotation, and we will continue our discussion on local rotation for the first half of today's lecture. And then we will talk about similarity between stress tensor, which we studied from lecture 1 to lecture 10, and strain tensor, which I introduced in our last lecture. So let me share the screen and then we can start with the lecture. Okay, so why is this creating problem? Some reason it is not allowing me to. Okay, now we are online. Okay, so I hope my presentation, my screen is visible to everyone. And with this belief, let me start. So this is what we were discussing in our last lecture. So if you recall, what we did was we considered what was known, and that was dx is equal to f dx. Remember that small x is the deformed configuration and capital X is the reference configuration, or you can say the initial configuration. And then what we did was we represented f, which was deformation gradient, in terms of displacement gradient, and that gives us I plus grad of u dx. So this is basically we are getting this by representing deformation gradient, which is f, representing deformation gradient in terms of displacement gradient. So that is what we are doing here. We are representing f, which is deformation gradient, as I plus grad of u, and I plus grad of u is your displacement gradient, right? So we are doing it, and then this grad of u is a second order tensor, and any second order tensor can be represented as summation of one symmetric matrix and one skew symmetric matrix. So what we do is grad of u, which is a second order tensor, we represent it as half grad of u plus grad of u transpose plus half grad of u minus grad of u transpose. So we take this part and substitute this grad of into the equation, and that yields dx is equal to I plus half grad of u plus grad of u transpose. And remember that this term is your strain tensor. So this is basically your epsilon. And since it is a second order tensor, we can write it like this. And then we have half grad of u minus grad of u transpose. And this term we represent it by using w. And then outside what we have is dx. So if we take the strain part outside, or if we separate the strain part, the final thing we had, and these are things we discussed in our last lecture, is epsilon dx plus I plus w dx. And then we discussed that this part, or to be particular, this strain tensor, so this part is responsible for straining the body. So this is the part which will result in deformation for straining the body. And when I'm saying straining, I refer to all the three types of strains, and those are longitudinal strain, volumetric strain, and shear strain. So this epsilon tensor is responsible for everything. And then we have this part, and this results in rotation. And when I'm saying rotation, it is rigid rotation. So this part is responsible for rigid rotation of the body. And what is rigid rotation means? Well, rigid rotation means that if we look into the relative position of particles within a body, the relative position will not change. However, each of the particle has displaced. That is what we mean by rigid rotation. So the body has rotated, the body has displaced. However, the body has not deformed. The body will not deform because of this part. Deformation of the body is because of the first term. And these are things we discussed earlier, right? So now, I mean, how can we say that this part is responsible for rotation? Well, for that we have Rodriguez formula, and this is what the Rodriguez formula looks like. So rotation can be represented as I cos theta, where I is a identity matrix, and then there is A sin theta, where A is a skew symmetric matrix. So let me write it down actually here. So I is identity matrix. So I is identity matrix. A is a skew symmetric matrix. Skew symmetric matrix. And then there is axial of A, which we will discuss today. And then there is cos theta and sin theta, where theta is the angle of rotation. Now, if we assume that the rotation is very small, as we have assumed for strain throughout this course until now, so if we assume theta to be small, what do we have? So this gives us two observations or two results. One is cos theta will become equal to 1, and the other is sin theta will become equal to theta. And then you go and substitute this term, so this will become 1 minus 1, so that will be 0, so this term will vanish. Here it is cos theta, so this will become 1, so you will have I from here, which you can see here. And then there is A sin theta, which will become A theta, because sin theta will become theta. So you get the final result, which looks like this. And clearly you can see that this is of the similar form as we have in our strain case, which is I plus W. So basically you can write that W is equal to A theta. And that is what we did. So we can say that this I plus W, this component is responsible for rigid body rotation. So these are things we discussed earlier. But now let us look into something new, something that we did not discuss in our previous lecture. So there is we are talking about rotation, right? So whenever there is a rotation, you have to tell me that the rotation is taking place about which axis. So we can say, so let me write it down here. Rotation or definition of rotation is incomplete without the axis of rotation. So if you want to find out, if you want to tell me that this is the rotation, you will also have to tell me that this rotation is about which axis, because there can be infinite number of axes in a 3D plane, and rotation can take place about any of these axes. So this rotation that we're talking about, which is resulting because of I plus W, is about which axis that we have to define. And there is a nice formula that does it. And the axis of rotation is computed as axial of W by magnitude of axial of W. So this expression is telling you something apart from the fact that this is giving you the axis of rotation. So as we just wrote that A, which is axis of rotation, is axial of W divided by axial of W. Now what is this sign? What is this? This is magnitude of a vector. This is magnitude of a vector, right? If this is magnitude of a vector, we can say that axial of W is a vector. So we can say axial of W is a vector. And what was W? W itself is a second order tensor, because it is like strain is a second order tensor. Similarly, W is a second order tensor. So W is a second order tensor. And there is another property of W, if you can remember. How does W looks? W looks something like this, is half del ui by del xj minus del uj by del xi, which means what can you say from this thing? You can say, if you think carefully, you can say that W is a skew symmetric matrix. The diagonals will be 0, because when it is II, these two terms will become equal, and that will give you 0. And otherwise, it will be like the diagonals will be opposite in sign of one another. So W is a skew symmetric matrix, right? So the term axial is generally used with skew symmetric matrix, and we will talk about what is axial in a short while. But for now, let me write down that axial is generally used in the context of skew symmetric matrix. So axial is used in the context of skew symmetric matrix, and axial is the one that gives you the vector in the direction of the axis about which the rotation takes place. So axial of W is a vector in the direction of the axis about which rotation takes place. So that is what axial of W is. I mean, in a theoretical sense. But now we will be looking into axial of W in a mathematical way. So given these points, we are going to look into axial of W in a mathematical way. So let us see. So axial. So this is what we will be talking now. Axial of a skew symmetric axial of a skew symmetric matrix. So this is what we are going to talk now. All right. So first thing is, and this talking about X one with trace mechanics whatsoever. It is a mathematical quantity. So we will be talking in terms of mathematics. So suppose A and B are two vectors. Now these vectors can be any vector, it does not matter, but we are going to assume two vectors. So you can write A as A1 I cap plus A2 j cap plus A3 k cap, right? And similarly, you can write B as B1 I cap plus B2 j cap plus B3 k cap. So this I cap, j cap, k cap, these are the unit normal vectors. We have already discussed about these things, right? And now let us say that C, which is a third vector, is equal to A cross product of B. So what we are doing is we are doing cross product. Be very careful. We are not doing tensor product or outer product. What we are doing is cross product, and cross product of two vector is also a vector. So just to avoid confusion, let me write it down here. Inner product. So these are things we have discussed in lecture 1 actually. So inner product or dot product of two vectors is a scalar. Remember, A dot B is a scalar, that is A1 square. I mean, if you look into the magnitude, it will become A1 square plus A2 square, A2 square plus A3 square, or A1 B1 plus A2 B2 plus A3 B3. But in any case, inner product or dot product of two vectors will give you a scalar. Outer product or tensor product of two vectors is a outer product or tensor product of two vectors is a second order tensor. This is also something we have discussed in our first lecture, the very first lecture. And lastly, cross product, and that is what we will be doing now, of two vectors is also a vector, right? So do not confuse between cross product and tensor product. There is a difference. But in any case, we are right now focusing on cross product. So C is A cross B, right? And if it is A cross B, how will it look? So first one is, if you look into the first column or the first component, it is basically the first component will leave out, so it will become A2 B3 minus A3 B2. What is the second component? The second component will be A1 B3 minus A3 B1. And the last component will be A1 B2 minus A2 B1. So this is how it looks. You can also write it in the using the unit normal vectors, and in that case it will look like a2b3 minus a3b2 I hat plus a1b3 minus a3b1 times j hat plus a1b2 minus a2b1 times k hat. So that is how it will look. Now there is a third way of writing it, right? Uh, and this is what we are concentrating on, okay? This is what we will be concentrating on. So let me write it down. So C is A cross B, and that is A2B3 minus A3B2 A1B3 minus A3B1 A1B2 minus A2B1. So this is the final result, and but we can also write it as a product of a matrix and a vector. The vector will be B1, B2, B3. In this matrix, the diagonal terms will be 0. And then the first term is actually, if you look into here, this is, so what is this location? This is 1, 2. So this will be A3. This is 1, 3. So this will become A2. And this is 2, 3. So this will become A1. So take the index position, and whatever is missing out of 1, 2, and 3, that will be the thing you will be writing there. So if it is 1, 2, you will write A3. If it is 1, 3, you will write A2. And if it is 2, 3, you will write A1. Now there is one more thing here. This one and this one will be negative. And now if you complete the matrix, this will become A3. And then this will become minus A2. And the last one will become A1. So if you do this product, you realize that you will be recovering whatever was missing actually, right? So for example, if you do the first one, you will get A2 B3 minus A3 B2. Do the second one, you will get A3 B1 minus A1 B3. So this is actually wrong here. And if you look into the third one, you will get A1 B2 minus A2 B1. So this is how it looks like. And this is skew symmetric matrix, right? This is a skew symmetric matrix. And now finally we are in a position to talk about axial. So let me clear up some space. The last line is the only thing that we need. So let me clear up some space so that we can proceed with the final step of this definition of axial. So this is kind of definition of axial. I mean, what we mean by axial, that is what I'm trying to explain here. And hopefully everyone here is understanding, or at least getting some sense. And if you are getting some sense, that is good enough, because when you read it again, you will understand, basically, if you are getting some sense. But if you're not even getting any sense, then there is a problem. Then probably you should write to me and I can explain it to you again at a different point of time. So in any case, okay. So now let us go back to the pen mode. So we have this skew symmetric matrix, right? Now axial of this skew symmetric matrix, let me call it A, okay? So axial of this A will be a vector which will give you uh, the actual, the column vector, the actual column vector, this one. So axial of this matrix will give you back this column vector. So axial of A is basically A1, A2, A3. So if you have this matrix, this Q symmetric matrix, what you will do? First, you will for the first position you will go to 2, 3, and 2, 3 is this one. You will take this value and substitute it here, but with a negative sign. For A2, you will go to 1, 3 and substitute that value as it is, and for A3, you will go to 1, 2 and substitute that value, but you will put a minus sign before that. So anyways, so we are now in a position to talk about the W matrix, and we'll talk about it. But first, let me write it down. So if you look into that A, which I just showed you, was 0 minus minus A. This is 1, 2, so minus A3. This is A2, A1 minus 0, 0, and then this is A3, this is minus A2, and this one is A1. So this is your A matrix, okay? And then axial of this A is the actual A vector, which is A1, A2, A3. Now, for the W that we have, which is a skew symmetric matrix, it looks like the first term is 0, the second term is del U1 by del X2 minus del U2 del X1. The half I can bring outside, okay. The third term is del U1 del X3 minus del U3 del X1. This diagonal is 0, this diagonal is 0, and this one finally is del U2 del X3 minus del U3 del X2. This is how the matrix looks until now, and now for this Q symmetric part, it will be opposite in sign. So this will become minus del U1 del X2 minus del U2 del X1. So one minus sign is coming, and that is the only change from definition of skew symmetry. Del U1 del X3 minus del U3 del X1. And lastly, this part, this will also come with a minus sign. So this will be del U2 del X3 minus del U3 del X2. So this is the skew symmetric matrix W. Now you tell me, by comparing with the above matrix, what is axial of W? Axial of W will be, so this location is 1, 2. So that means this term will go into the third location. So this will become, the third one will become del U1 del X2 minus del U2 del X1. But now there will be a minus sign before that. So this will become minus, this will become plus. This is 1, 3. So this will go into the second position and without any sign change. So directly it will be del U1 del X3 minus del U3 del X1. And lastly, this 2, 3 will go into the first location but with a minus sign. So this will be minus del U2 del x3 plus del u3 del x2, and this is your axial of w. What is missing is 1 by 2, this term. So this is what axial of w means. And this axial of w you can use this axial of w to compute or to get the axis of rotation, because just to recap, axis of rotation is axial of w divided by magnitude of axial of w. So basically, this is the direction, and then we are converting it into a unit vector. That is what this magnitude of axial of w is doing. So this is how you can compute the axis of rotation. The rotation value is I plus w, so that you can use, and that will rotate about axial of w, right? So exactly. So this is what the formula is. And what is axial of a skew symmetric matrix? That is what we discussed until now. So now we can proceed further. This is what I just wrote. So this is what we have discussed now. So this is how axial of W will look like. And then let us do a simple example. Okay. So suppose you have two functions f1 and f2, which will give you displacement uh, in the u1 direction and u2 direction, right? So let me draw it, and that will help us understand what is happening. So this is your initial configuration. So there is a point here which is x, and then this is my deformed configuration. That point capital X has now moved to small x. So this is your capital X vector. This is your small x vector, and this is your u. Now this u is also a vector. It will have three components. So this u vector is u1 I cap plus u2 j cap plus u3 k cap. And similarly, you can write x as x1 I cap, x2 j cap, x3 k cap, and small x as small x1 I cap, small x2 j cap, and small x3 k cap. So that is what you can do. And now what we are doing is we are defining a function which will give us this component, and that is u1 is f1, and it is function of x1 comma x2. u2 is f2, which is function of x1 and x2, or rather capital X1 and capital X2, let us say x1 and x2, and then u3 is 0. So basically, what can you say from this, that u3 is 0? You can say that we are working in a 2D plane of frame. So if my initial body was something like this, the deformed body will be something like this. So everything is going to happen in a plane. So we are working with 2D. This you can say directly from this f1 and f2. But we are going to, or we will try to re-establish this fact by finding out the axis of rotation. So just from intuition, what can you say? If u3 is 0, so everything is happening in a given plane, and in that case, the axis of rotation should be your third axis. So u3 should be the axis of rotation, right? This is what you should get from intuition, because u3 is 0. So that means nothing is happening in the third direction. Everything is happening on a given plane. And therefore, whatever rotation is there is about this third axis. I mean, if you think of the screen as a plane, so whatever I am drawing, that rotation is about is coming perpendicularly out of the plane, right? Now let us see whether we get this result from the axial which we just now discussed. Okay, so if that is the case, if u1 is f of x1 comma x2 and u2 is f2 x1 comma x2 and u3 is equal to 0, then what will be my strain matrix? So the strain or strain tensor, you can say. So the first term will be del u1 del x1, right? The second term will be 0.5, so half del u1 del x2 plus del u2 del x1, and for the third term it is del u3 by del x1, so that is 0, and also del u1 by del x3, which is also 0. So this term is 0. This since this is a symmetric matrix, this one will be identical. So let me not write it down. What I will do is I will just point it out. Okay, and so what I will do is point it out. This term will come here. This will be 0. This will be del u2 del x2, and this will be half. So let us see. Del u3 by x2. u3 is 0, so that will become 0. And then u2 x3, u2 is not a function of x3, so that will also become 0. So by symmetry, this is 0 and this is 0. So in essence, this is your strain matrix. Okay. And then what will be your W matrix, which is the rotation one. So the W matrix will be, the diagonals will be now be 0. And then this will become half del u1 del x2 and then minus del u2 del x1, right? And this is 0, 0, and then this is 0, 0, and this is negative of this value. Negative of the value. I mean, not negative of negative, only negative. So this is negative of what is in 1, 2 location. So 2, 1 will be negative of that. So this is my W matrix. So then what is axial of W? So axial of W will be a vector, right? So what will be there in the first location? First location is 2, 3. So this is 2, 3. So this is 0. What will be the second location? 1, 3. This is 1, 3. So that becomes 0. And what will be in the third location? 1, 2. This is 1, 2, and with a negative sign. So minus half del u1 del x2 minus del u2 del x1. So you can see that only the value in the z location or the third component is there, which essentially is telling me that somehow the rotation will be about the z axis. Rotation about the third axis. So this is somewhat, I mean, what was expected, we are getting that result from axial of W. So this was a very simple example, but simple examples are often the good examples for explaining concepts. Rotation about the third axis, right? So let us see. So this was the epsilon matrix, this was the W matrix, and this is what we just derived. So W is axial of capital W, and that is basically only having the third component, that is the Z component. So which means rotation is going to take place about the Z axis, right? Now we are going to solve another problem, which is the same problem, but an extension you can think of it. So let us see. So we have our strain and all those things. So we have our strain and W and axial of W. So all these things we have done. So what we are going to do is we are going to say this is the initial configuration, and then there is some rotation, right? So this is the E1 direction, this is the E2 direction. So what is gamma for this one? Gamma is 2 times epsilon xy. So that will give you del u1 del x2 plus del u2 del x1. This is what gamma is, or gamma xy is, right? And then what is epsilon xy then? Epsilon xy is half del u1 del x2 plus del u2 del x1. So this is what your strain tensor, component of strain tensor, let me write it down. So shear component of strain tensor, right? So E1 is basically the shear component, not E1, epsilon xy is the shear component of the strain tensor. Now, if we look into the rotation, what will be the rotation? Let us see. So let us write it as wxy. I can write it like that, and that is half del u1 del x2 minus del u2 del x1. Right. So your what should I say this? Your rotation, the overall rotation of this is half del u1 del x2 minus del u2 del x1. Now let us see what is happening here. So what is rigid body rotation? Suppose we have x and y. So if strain is 0, what will happen? This line will come here and this will come here. And if this angle was 90° and there is a rigid body rotation, this angle will also be 90°. So when there is a rigid body rotation, the two line elements will move in the same direction. So for rigid body rotation, the two line elements move or rotate in the same direction. And that is only when you can say that it is a rigid body rotation, right? Because only then the relative angle, which is 90°, is remaining same. However, for strain, the rotation should be in the opposite direction. It can be, if they are equal, they will have to be in the opposite direction. So the rotation will be in opposite direction. So keep this point in mind that when there is a rigid body rotation which is happening due to W, the rotation will be in the same direction for both the line elements. Whereas when there is a strain, one of the line element will move in the clockwise direction, the other will move in the anti-clockwise direction. So that is what the point was here. So now what we are going to do is, we are going to take one of these element, say delta x1, let us say, and we are going to show, or we are going to establish some result that we already know. Okay, so let us start. And this is the last part for today's lecture. So this is the one, and this is the rotated one. So let us say this is x, this is y direction. So the line element is the dx, and this line element is dy. Okay. And now what we are going to do is gamma, which is 2 epsilon, I mean xy you can write down here, is del u1 del x2 plus del u2 del x1. So what is this gamma? Change in angle between x and y. So basically this angle plus this angle, right? Now, which means I can say that the due to shear strain, and this is a very key word, because this if you miss this word shear strain, you will get confused with something we have derived earlier. So due to shear strain, rotation of dx, due to shear strain, what is the rotation of dx? The total rotation is del u. This is the total rotation, right? So if we consider only rotation of x or dx, that is half of that. Del u1 del x2 plus del u2 del x1. And this is only because of shear strain. Remember that part. Only because of shear strain. So this is the rotation, and this is in the anti-clockwise direction. So I will write AC. Okay. And then due to rigid body rotation, which is W, what is due to rigid body rotation, or rigid body, I mean due to W basically, rigid rotation of dx is half del u1 del x2 minus del u2 del x1. And this is in the clockwise direction, right? So then, therefore, total rotation of dx. And what is the total rotation of dx? Rotation due to shear plus rotation due to the rigid body part. So, and since they are in the opposite direction, we are going to subtract. So it will be half del u1 del x2 plus del u2 del x1 minus half del u1 del x2 minus del u2 del x1, and the final result is del u2 del x1. So this alpha you are seeing, which is the total rotation of dx. So this alpha is del u2 del x1, and in the clockwise, anti-clockwise direction. Similarly, if you do this beta, you will find it to be del u1 del x2, but in the clockwise direction, right? So this is some result that we already know actually. I mean, this was one of your homework. Remember, I asked you to do it from geometry, but instead of doing it from geometry, you can also do it like by using the rotation and the shear strain component, right? So that is what we talked about. So total rotation, which is rotation due to shear component plus rotation due to the rigid body rotation, is this one. And when you talk about del x2, it is this one, and the minus sign is showing that this rotation is in the clockwise direction, while this was in the anti-clockwise direction, right? Now, last thing, okay, so there are some other things I want to discuss. So let us see. So this is actually all the things I wanted to discuss about local rotation. Okay, and now let us move to something interesting, and that is similarity between stress and strain. So first is transformation of stress. You remember we learned about transformation of stress in our fourth lecture, and this was the formula for transformation of stress. Normal stress was sigma n dot n, and for shear component it was sigma n dot m. And when we talked about shear, about strain, the formulas we derived was epsilon n dot n and 2 times epsilon n dot m. And what is this epsilon? Epsilon is half of grad u plus grad u transpose. So that is what epsilon is, and sigma is, this sigma was summation ti with tensor product ei, right? So that is what sigma was. And this n here is plane normal, while this n here is a material line, or you can say a line element. But apart from these two facts, the formulas are exactly same. For gamma, there is one additional term, and that is because if you remember, gamma xy is actually twice epsilon xy. So that is from where this 2 is coming. But other than that, they are same. Symmetry. The second point is symmetry, and we know that stress tensor is symmetric in nature. Tau xy is equal to tau yx, and that is something we proved. And similarly for strain tensor, if this is the form, it is going to be symmetric. So both are symmetric in nature. We talked about principal component. You remember the characteristic equation? This was the characteristic equation we talked about. And from there, we can compute the principal stresses. Similarly for epsilon also, there is a characteristic equation. And this J1, J2, J3, these are known as the strain invariants. So I1, I2, I3 are the stress invariants. J1, J2, J3 are the strain invariants. And then if you solve this equation, you can compute the principal strain similar to how you compute the principal stresses. And if you compute the principal strain, you can also compute the maximum shear strain, like how you compute the maximum shear stress. Now, the maximum shear components make 45-degree angle with the principal plane, and this is true for both stress and strain. In both the cases, the angle between the maximum shear and the principal direction is 45-degree. We talked about Morse circle when we were talking about stress. Morse circle is equally applicable for strain as well. So the same thing is applicable. And then invariance, like just now I talked about I1, I2, I3. And similarly, I talked about J1, J2, J3. Same thing. I1 and J1 are computed in the same way. Trace of the matrix. If you are taking trace of the stress matrix, so for example, if I take I1, it is trace of sigma. J1 will be trace of epsilon. So like that. Similarly, I2, J2, I3, J3 are also similar. Last part is decomposition. So if you remember, if we have a stress, we can write it as hydrostatic stress plus deviatoric stress, so which was like sigma HYD, sigma HYD, sigma HYD, and everything was 0. And then plus it was sigma XX minus sigma HYD, and then the other components will as it is. I mean, sigma YY minus sigma HYD, and sigma ZZ minus sigma HYD. And then it was sigma XY, sigma XZ, sigma XY, sigma YZ, sigma XZ, sigma YZ. So like we could decompose into the hydrostatic stress and deviatoric stress. The same thing you can do for strain. So if you do for strain, it will become, say, epsilon, epsilon, epsilon 0, 0, 0, 0, 0, 0 plus epsilon xx minus epsilon, epsilon xy, epsilon xz, epsilon xy, epsilon yy minus epsilon, epsilon yz, epsilon xz, epsilon yz, epsilon zz minus epsilon. And for this part, see the trace of this matrix is 0. So this deviatoric part, deviatoric strain will not result in change in volume. So there will be no volumetric strain because of the deviatoric part. The volumetric strain is always due to hydrostatic part, right? So yeah, this is something we discuss. And lastly, we talk about an alternate definition of strain, so or shear strain. So we talked about shear strain, and that was defined as change in angle, right? So let us take a special case where U1 is equal to alpha x2 and U2, U3, these are equal to 0. So there is only 1. So if I draw this green line you are seeing is the initial configuration and the magenta line is the final configuration. So if this angle is gamma, this is my shear strain. We know that change in angle, right? So total change in angle is, you can think of it as shear strain. Now, if I have to compute tan of gamma, that will be, so if I take this angle, this one, that is alpha x2 divided by this length, so alpha x2 by x2, so that is equal to alpha. Now, if we go into the small strain consideration, in that case, tan gamma is approximately equal to gamma, and in which case gamma is equal to alpha. So gamma was the shear strain. So, and alpha was the ratio. So what you can say is that shear strain can be defined as change in length in the lateral direction by the actual length in the perpendicular direction, that is the longitudinal direction. So that is another definition of shear strain. I know this last part I covered a little faster, but these are things you probably already know. But still, if you have some doubt in this part, specifically the similarity between stress and strain and alternative definition of strain, do let me know and I will cover it again for you separately. Okay. But I don't think you will have any problem if you have understood the stress part, because this is kind of repetition of what was covered in the strain part. Okay. So we'll stop here and then we will meet again in the next lecture where we will do something new, something very interesting we'll do. Okay. So thank you.